the stability, which was the competition was about. So, and I would like to start with the plan of our presentation. So basically, our presentation is divided into three main parts. So the first one is about the custom loss, which we developed specifically for this competition in order to try to address the stability problem. So the second part is about a very important step, a very important process, as other participants have already mentioned. It is feature engineering, also about feature selection, aggregations, processing some categorical variables, and so on and so on. And the third part was about the training methods, how we fitted our models, how we ensemble them, and some important details, some important additional details, which are also worth mentioning. So to begin with, just a few words about the team, about who we are. So we graduated from the same university, from the same mathematical department some years ago. And since then, we have been working in the data science field. So the reason why we decided to participate as a team was just that we graduated from the same university. We knew each other. We are friends, actually, and we decided that it's a good idea to participate in this competition as a team, participate together. And by the way, there was also another reason why we decided to participate as a team, because creating this custom loss was quite labor-intensive. It was necessary to check the analytical derivations. It was necessary to prepare some unit tests in order to make sure that our custom loss works correctly as expected, and so on and so on. So it was quite labor intensive. That is why it was necessary to participate as a team of 4 people, of 4 members. So the first main part of the presentation is the structure and the core idea of the custom loss. So let me remind you that the stability metric used in the competition consists of 3 main parts, consists of 3 terms. The first one is about the Rockow score. The second one is about the decay effect, the decay in the performance of our model. And the third is about the stability of the Rockow scores across different weeks. And at the beginning of the competition, we wanted to try addressing all of these 3 terms together. I mean, simultaneously, to address each part of the stability metric. Unfortunately, when the week now was removed, it became quite difficult to address the second, but probably the most important part of the stability metric, which is about the decay effect. So we decided to focus on only the first part and the last part of the stability metric. Indeed, if there is no trend in Gini scores, you have a higher chance that your Rockow scores are stable and there is no decay in the performance of the model. So it was the main hope of our team that probably making Rockow scores as stable as possible can help you make the decay effect just a bit less or something. So that is why we decided to focus on the first term and on the last term of the stability metric. The first term, by the way, is the mean value of Gini or approximately Rockow scores, something like that. However, I would like to remind you that using some standard libraries like sklearn or like GBM, so they don't allow you to focus on Rockow scores directly. Unfortunately, this metric is not differentiable, so it is not possible to address Rockow scores directly. So what I would like to say is, even if a stability metric consisted of only the first term, it would also challenging to minimize Rockow scores directly instead of minimizing log losses or something like that because standard libraries offer you minimizing log loss or some standard losses, but not Rockow scores or Gini scores. We found an interesting paper, which is referred by the link in the presentation, how one can address the Rockow score directly of a binary classifier. It is quite straightforward, and I strongly recommend you read this paper because it is really not very difficult. It's quite simple to understand. It's quite straightforward. So there are some additional plots in order to help you realize how we can address the minimizing of the Rockow scores. But the basic idea is to calculate the number of inversions of our samples. So we got our training set, which consists of positive and negative samples, since we solve a binary classification problem. So we have positive and negative samples. And the UI on this slide stands for the approximate number of inversions. What does an inversion mean? So one inversion is a situation when a negative sample gets a higher score than a positive sample. So this situation is called an inversion. Indeed, if you sort all your samples by their model score, by the output of our ensemble, by an output of a model, they can be sorted by their model score, by their anomaly proba or something like this, by the model output. And if a positive sample gets a score which is less than a negative sample, the situation is called an inversion. We can calculate this number of inversions across the whole test set. So that means that we compare every pair of a positive and a negative samples, and we sum all of these inversions together. After that, we can normalize the sum in order to make it in the range from 0 to 1, in the unit range. And the second idea, so this is the first idea of how one can address the Rockow score directly. So the second idea on the slide is that we can divide our training set into small subsets, which are called U1, U2, and UM. There are M different subsets. There are M different groups, which are, by the way, consecutive groups. So, for example, the first U1 corresponds, for example, to the first week, or to the first and the second week. But okay, so U1 corresponds to the first week, U2 corresponds to the second week, U3 corresponds to the third week, and so on and so on. So we divided our training set into M subsets, and in each subset, we can calculate the number of inversions. After that, we can calculate the average number of such inversions across different subsets. So this is the core idea of the custom loss. So as I said, UI is the number of inversions in one subset divided by corresponding value to normalize it into the 0-1 interval. And after that, we can sum all these sub-losses into one big loss, into one main loss, in order to calculate the stability loss. So the main problem is actually to calculate the first and the second derivatives of our loss, because in order to be able to use a custom loss in a framework like LibGBM or Escalor, it is necessary to calculate analytical first and second derivatives. By the way, we tried to make it in a numerically, but unfortunately it didn't work because the number of the dimension of your space where you would like to minimize your custom loss is quite high. So this is about thousands. This is about thousands. So in such high dimensional spaces, numerical derivatives do not work well. So that is why it was necessary to calculate all first and second derivatives analytically. Yeah, so as I have already mentioned, so the first big problem with the custom loss was quite labor-intensive analytical derivations of derivatives. But there was another problem. The second problem is when you use a custom loss, unfortunately, standard optimization methods like transferring your computations onto the GPUs, unfortunately, they don't work. So it was necessary to optimize, that means to speed up the computation of the custom loss in order to make it possible to train a model on within a Kaggle session, which is limited to 12 hours. So it was also a problem because it was necessary to speed up our custom loss several times in order to make it possible to train it in less than 12 hours. So the first problem is first and second derivatives, and the second problem was the performance. So we have finished with the first main part of our presentation, and let me move to the second part. Our pre-processing stage, which is quite important. We could see it from the previous home credit competition, where it was really a key to the winning solution. So our pre-processing stage is divided into 5 main parts. So the first part is quite simple. So find and remove duplicated columns. In this data set, they really exist, duplicated columns. We can just remove them and proceed to the next step. The second step is handle categorical features. We decided that we can keep only 20 categories for each categorical variable, not just 200, 100, just 20, and replace all other categories with additional 21st category, which is called like others or another category. And we observed, when we did it, we observed that we didn't get any significant decrease in our model performance. So we decided that probably keeping not more than 20 categories for our categorical features can also help address our stability and probably make the probability of overfitting is less probable, is less feasible. So the first 2 steps are quite straightforward. So we find and remove duplicated columns, and we replace 2 rare categorical values with special category, which is called others. But the last 3rd steps are a little bit more difficult. So I would like to explain them in more details. So the 3rd one is apply aggregations. And what is an aggregation? So we observed that in this data set, there are some columns which contain the same information. So a good example would be a birth date of a person. Obviously, one person can have only one true birth date. However, in some columns, this date can vary. So we decided that probably to get the most reliable value of the birth date of a person, different columns contain the information about their birth date can be united, can be combined together in order to produce only one value which is more reliable. So we can basically squeeze several columns contain the same information into one reliable column, making the number of features less, and probably it can also help us address the stability problem, because we decrease the number of features and we construct one more reliable feature instead of 3 or more, which are probably a little bit less reliable. By the way, the same process was applied to calculation the mean value or some other values. So the fourth step was to produce some compound features. For example, the sum of two features or the difference of two features. Why we thought that it is necessary to do that? Because tree-based models like LightGBM, XGBoost, or others, what they do, so they basically compare one feature value with a particular threshold at each tree node. However, doing this, they are unfortunately they are not able to compare the difference of two features. For example, it can be interesting to calculate the amount of money a person has per month without the amount of money which this person is supposed to pay his debts. In other words, a person gets some money as a salary, and some part of their salary should be sent to banks in order to pay the debts. And what is interesting is the amount of money the person has after this process. The person has to cover other needs or to buy foods, I don't know, etc. So that is why we decided that it is necessary to produce some additional or compound features to calculate new features, which are differences, which are sums, products, or anything else from base features, from the features we had in this data set. So it was the fourth preprocessing step. And the last but not least, after the generation process of new features, it was necessary to select the most reliable or the most important features. We also wanted to keep the number of features not very big, not very large, because we believed that the fewer features we have, the more stable our model would be. So that is why we selected a primary set of features. We called them a primary set, which consisted of approximately 50 features, if I'm not mistaken. So we did it based on the common sense. For example, it was obvious for us that the feature called price of the loan is quite important and is definitely worth including in the feature set. And based on some other information, for example, the feature weights of our preliminary models, we selected some primary features. 50 features are the most important. And after that, we tried to add new features one by one and observed whether it leads to the improvement in our ROCAUC score or not. Some features, by the way, can lead to decrease your ROCAUC scores. That's normal, and that's called overfitting. So we wanted to select only those features which can lead to the improvement in the ROCAUC score. After finishing this process, we selected 262 features to train our models using default loss and using our custom loss. So we used only 262 features. Let's move on to the last part, the third part, which is about the training process. As I have already mentioned, it was quite necessary to optimize our custom loss several times in order to make it possible to train one fold model within one Kaggle session. So training LightGBM and CatBoost models were quite straightforward because they use the highly optimized standard losses like log loss, and our LightGBM model with custom loss takes approximately 11 hours to train one fold, each fold out of 7 folds. Here is the feature importances of our model. And we can see, by the way, that the most important feature is called AGG birthd, which is the aggregated birth date of a person. By the way, that what also is sign that our idea to aggregate some features into one reliable feature was prominent, was quite interesting, and it confirms, so such plots confirm that aggregations, that aggregation a few features into one reliable feature really works, because we can see some other features which have the AGG prefix, like the first feature, the sixth feature, which is AGG Credit Bureau Queries L, and there are some other features prefixed by AGG and this feature importance plot. And there was another confirmation why probably our idea with applying aggregations work in this case. Also, we tried to avoid situations where a couple of features become dominant in comparison to other features, because in many cases, it is a sign of overfitting to these a few features and a sign of just overfitting. So we would like to make this plot as uniform as possible. Just a few words about our findings and about some unexpected results. So the first one was about the recovery of the time based on refresh date, based on the feature which is called refresh date. However, it is worth mentioning that we could recover not more than 50% of the dates in the test set in this way by analyzing correlations of different date features between each other. So due to this fact, it was also necessary to make your model as stable as possible and as good as possible, because we couldn't fully rely on the recovery of the dates. And it is also worth mentioning that when we decided to construct new features, as I said, compound features, some of them gave Rockhook score more than 0.7. If we use feature values directly as predictions, because when you are focused on maximizing your Rockhook score, it is not compulsory to keep your predictions, to keep your model predictions within the interval 0, 1. So you can make them anything you want. So they can vary from 0 to 1,000, from 0 to 5,000, from 1,000 to 10,000, any way you want. So in this way, you can use one feature values directly as your predictions. By the way, we tried it on Kaggle, and it successfully calculated some score. So it was also confirmation that it is possible to use one feature values directly as model predictions if you are focused on Rockhook scores. And there were some features which gave you more than 0.7 Rockhook. And it was also confirmation that probably it is really worth constructing new compound features, because we can see that the first feature is the sum of two base features. And the other features are also some compound features. And I would like to remind you that the whole feature set, which consisted of 262 features, gave us approximately 0.85 rock oak. But using only one feature, you can achieve 0.7 rock oak. That was probably one of the most surprising things for our team.